Hello everyone, welcome back to my channel. In our last couple of videos we have discussed the Mnist classification problem and we have implemented a basic neural network in both TensorFlow and NumPy. Now in this video we will implement the similar network in PyTorch and we will see how different it is from the TensorFlow implementation. So for PyTorch the package we need to import is Torch. Along with the Torch, we have seen in the TensorFlow implementation as well, Mnist dataset is part of the TensorFlow framework in the datasets. Similarly in PyTorch also, the Mnist dataset is part of the Torch Vision datasets module. So the Torch Vision is the module where you have all computer vision related resources are available. Okay, so we have imported both Torch and Torch Vision. So we'll quickly see the version of Torch. So this is the latest one, Torch 1.12. Now the first thing I will do is load the dataset. So as I mentioned, Mnist dataset is part of the Torch itself. So we need to load the dataset from torchvision.datasets. So this particular place are having most of the computer vision datasets. So out of which we need to take Mnist here. Now once we import this, we need to load the Mnist dataset, right? So from Mnist dataset, we need two categories. One is the train part, one is the testing part. So both you can download separately in case of PyTorch. So let's say I want to download the train dataset. Now what I need to do is Mnist, this is my dataset. Now here I need to provide the path where I need to download. So I am downloading in my root location. Now download is true, and then if I want to use the training dataset, then I need to keep train flag as true. If I want to download the test dataset, I need to just make that flag as false. I need to make this as false for getting the test dataset. Now this will download the Mnist dataset into my local as well, and it has loaded the dataset into these variables. Now we will see the sample dataset, how it looks like. So let's say I want to see one sample from training dataset and I want to check the 10th image, and 10th location is the dataset location, the 10th entry, and in that 0th index is the image. So you can see 3 is the 0th index. Now the same thing we can take and we can just check the label here. So label is 3. So you can see this, the dataset is arranged like this. The entries are the first index and 0 is the image and 1 is the label. Now we know that okay, this is the image. So we just want to see the dimension of the image. So first thing what we will do is we will know what is the type of the image, because sometimes it might not be the actual image type. It might be tensor or it might be something else. Okay, so here our image type is PIL image. So now I just need to get the size of it. Data train 00.size. So size is the one which will give me dimensions in PIL. So you can see the image dimensions are 28 by 28. Now we need to normalize our image because these pixel values are ranging from 0 to 255. So we need to normalize this image. Along with that, to our neural network, as I mentioned earlier, we are trying to build a simple two-layer network, and it is a dense network. It is not any CNN. So when you want to give any input to the dense network, it should be in a vector form. So we cannot directly give this 28 by 28 as the input. So that's why in TensorFlow version also, what we did is we have flattened the array before passing to the network. So if you see here, we have a flattened layer which is actually taking 28 by 28 and it is flattening that into 784 because 28 by 28 is 784. So we can do this as part of the network itself. Otherwise, there is another option. We can do this as part of the dataset loading itself. So in PyTorch, there are actually transforms. So PyTorch Torch Vision has transforms where you can apply lot of image transformations like normalizing the dataset as well as changing the dimensions, or you can apply some other augmentations. So all these kind of things you can do via transforms, and this one you can do while loading the dataset itself, like how we are loading it here. the dataset Mnist root the same place, we can actually add transforms here, and it will apply the transforms on top of this dataset and load into these variables directly. So let's see how it works here. Now first of all, I'll just need to import the transforms. So the transforms also are part of Torch Vision. Okay, so first transform I need to do is I need to normalize the data. So for normalizing, I will write my own function. If you want to write your own transformation function, you can pass it as lambda function. So that's why I'm doing it here. And one more thing is our images are in the PIL format. Now I need to convert those into tensors. So for that we have a 2 tensor transform. So these are all the transformations inbuilt in the PyTorch. So if you have multiple transforms, you can compose them in a single command using compose. So for that we need these things. Now once these are done, now I'll just define my transform definition. So transform is a combination of this lambda function and 2 tensor. So I'll just show you how to write this one. Here I need to pass a list where we need to give all the transformations, where we need to write all the transformations we want to apply on our images. So first thing is I want to apply 2 tensor. This is my first transformation. First the PIL image I am converting into tensor. Once that is done, now what I need to do? I need to normalize the image. So for that what I will do is I will actually do lambda, which is my custom function. I can write my own function in lambda transformation. So this is my lambda, whatever image is there, image by 255. This is what I need, right? Done. Then the next one is I will actually do this flattening also here. So I am converting 28 by 28 into 784 as a single pixel. So for that also I can directly do lambda here. Now what I need to do is I will take image as the input, and then what will be my output? My output is image.view. So you can simply do view with your image. So it will actually rearrange the dimensions to view it as 784. So this is nothing but your flattening. These are my transformations. Now I need to apply these transformations on top of the dataset. So I can do this thing while loading the dataset itself. So I'll just take these statements where I am downloading the dataset. I'll just re-download the dataset just to show you how you can do. So I'm copying these things. So now think that you are freshly downloading the dataset now, and while downloading the dataset itself you want to apply these transformations. So you can directly do one more variable, transforms is equal to transform. Okay, so now this particular thing, transform is the inbuilt name, the argument name for this Mnist function. So for the same thing I'm actually sending my own compose transformation. So now when I run this one, while downloading itself, it will actually apply these transformations to these datasets. So we can see that. Okay, so it has downloaded these datasets. Now if I see data train, so now I have data. Okay, let's see this one. Okay, you can see that all these are normalized values. These are not from 0 to 255. These are normalized values. And let's see the shape of it. Because I converted to tensor, I can use shape here. So you can see it is 784. Because my data I have converted into 784 from 28 by 28. So that is from the dataset loading. Now we will build the model. So for building the model, what we need to do is we need to have NN module. So NN is actually the neural network module available where all the network layers like fully connected layer, activation functions, CNN layers, all of these are available as part of that module. So for building the network, we need to load that module. So import NN. Along with that, optimizers are available in Optim. So we are done loading these things, importing these. Now we'll build the architecture. So for that, first I will do class. I'll just do model, for example, and this should be inheriting from NN module. Okay, because NN module has the implementations of whatever the layers we are trying to use for their backward passes, gradient computations, all of them are implemented as part of this NN module. This is similar to the TensorFlow Keras model. When we are building our own class, we are actually inheriting from TF Keras model. The same way, when we are building our own model, we are actually inheriting from NN module. Okay. Now we need to write our init function. Now I need to define the layers. So in TensorFlow we have done first defining all the layers here, and then after that connecting in the call function. The same way we will do in PyTorch also. So for that I need to define all the layers first. So I am taking the layer sizes as the input here. So I can do the same thing here. Sizes as the input. So that I can give as an argument directly how many layers and how many neurons I need in each layer. So I'm building only 2-layer network. The output layer is, of course 3-layer network. Output layer is 10 neurons and remaining are the respective neurons actually. So let's see how to build this one. So I'm just building the first hidden layer. Hidden layer 1. So for building the hidden layer 1, I need a fully connected layer which is known as linear in PyTorch. In TensorFlow it is dense, whereas here it is linear. Only naming conventions are different, but the way the models are built is similar here. So now for PyTorch we need to provide what is the input channels and what are the output channels for this particular layer. Input channels are 784 because my images are 784, and output channels I can provide how many I want, how many neurons I need, I can provide that. So let's suppose that I am sending sizes as 128, 64, 10. So 3-layer network, each layer with these many number of neurons. So now it will go 128 here. So now after this I will do first activation function. So I'm just using sigmoid here. So you can use sigmoid, tanh, relu, whatever you want to use. It's your wish. So nn sigmoid here. So I will use the same thing for the second hidden layer. The input is actually sizes of 0 and the output is 1. So here it is, I'll just write it here. Here it is actually 784, 128, whereas here it is 128, 64, and this is actually activation 2. And if I want to do the same thing for the output layer, this will be 68 by 10 because 10 is my output layer number of classes. Mnist has 10 classes, and in the it is multi-class, so I'll just use softmax here instead of sigmoid, and then I will do this one. So for softmax we need to provide the dimension. I will provide the first dimension, the dimension 0 and 1 I will provide. So this is done till here. Now once the network is done, we need to calculate the loss also during the training, right? So I'll just initialize the loss also here. So loss, it is cross entropy loss. Okay, and then what is the optimizer? Optimizer, I can use any optimizer. So I have optimizers are part of optim module, and I am using Adam here. So for this optimizer, I am sending the parameters. So these parameters are actually whatever the network we are building, whatever the weights are there, learned weights, those are going as parameters here. So this is inbuilt in the NN module class. So that's why we are inheriting here. So that's why you can directly use this as part of this one. This is part of your parent class. Now we have built all the modules required for building the classifier. So we will actually build the network now. So for building the network, we have forward function. So for forward function, whatever my inputs are coming, those will come here, which are images during the training. Now for connecting, I just need to call these layers. hidden layer 1, and then inputs will go here. Okay, and then x is equal to self.activation1 of x. So if you see here, my inputs are going to hidden layer 1, and whatever output I am getting, that I am passing to first activation, and whatever output I am getting here, that I will pass to second hidden layer. So we have gone through all the network. So we have connected the whole network. So we will write the function for training loop. So that also we can pass here itself. Otherwise you can write your separate training loop, or if you want to write it as a function and call it as a function later, you can actually write the function here. So I am writing a function called fit here, because the fit is similar to TensorFlow fit. When you build the model after compilation, this is the whole training loop. This fit is taking care of the whole thing in TensorFlow. There is no definition for fit in our model definition here, but in PyTorch there is nothing like that here available. So we are writing our own fit function. So self dot, let's say I have x and y. These are my images and labels. This is the training loop. So I am getting the ground truth. Now before starting the training, I need to actually reset the optimizer. So zero grad, what it does is it will actually make all the gradients of these parameters, whatever the learned parameters are there, the weights, for those things, all the gradients, it will reset to 0. So it will happen for every epoch. So now I am doing the prediction here. So self dot forward. So forward function, I'll pass x, right? So it will do the model prediction. By the end of this y prediction, my x here, it is coming as y prediction here, which is the output of softmax. Now I need to calculate the loss, because I have the y prediction and I have the ground truth. So I'll just do loss. We have the loss function already. So for that, I will just do prediction and y. Fine. And I need to do backward computation. Okay, this is the backward propagation. So if you observe, in TensorFlow we did not write any of these steps. This fit function is taking care of all of this, but now we need to write our own function. So generally the training loop involves loading the dataset, passing to the model, forward pass, and whatever the predictions are coming, we need to calculate the loss. Once you have the loss, you need to back propagate that loss to your whole network from end to the beginning. And after you do the back propagation, during the back propagation, all the gradients will get computed. And once the back propagation is done, once you have all the gradients, we just need to apply the gradients to update the weights. So that is what happens in step function. So if you see here, this is actually calculation of gradients. This is back propagation. Okay. And this is based on your optimizer updating the weights. Okay, this finishes your training process. Once you updated the parameters, then you need to go with the next iteration. So I'm just returning the loss value for my stats. So I just need this one for printing the logs, that's it, nothing else. So dot item will give me the actual value. If I take loss directly, it will have the that it is actually the PyTorch variable graph. Whereas if I take only item, that means only the actual value for that it will provide. Okay, so this is the total definition. So anything else I require? This is the initialization of the network, the forward pass, which will provide the connectivity, and actually the training loop. Maybe I need the testing also. So for testing, I need the prediction. So I'll just do prediction function. Then I will just need x here. Okay. Otherwise, I can write evaluate function also. In TensorFlow, there is evaluate by default available, but we can write our own evaluate function here itself for doing the testing as well. While doing evaluation, we need not to calculate any gradients. So by default, when you are computing the graph, it will actually keep all the connections details in the variables, because for calculating the back propagation, you need all those connection informations. But when you are doing only testing, you don't need back propagation. So we just need to pass this no grad. When you pass this no grad, then it won't save all those variables, all the computation information in the graph. So we don't need that. So we'll just do this one. And what I need here, I just need to predict the output, right? So I'll just do self dot forward and x here. So once I get the x, maybe I'll just do the maximum output, because this is actually softmax output. So I need the maximum. What is the argmax? What is the index where I have the maximum probability score? So argmax I will do with axis equal to 1. The last axis I need. That's it. So with this one I will just return it from the predict. Done. Okay, so this is my predict function. Similarly, I can use evaluate function, which will calculate the accuracy percentage also based on the ground truth. So we can pass the whole test data set here. So let's say test data loader. So here I need to write a loop. So for x comma y in test data loader, so it will give me one by one the image as well as the label. So first I need to do y underscore prediction is equal to self dot predict, right? Self dot predict x. So it will give me the index where the class information where the maximum probability score is there. So that is my y prediction. So the same thing I will get in capital Y also, which is actually my ground truth. So I will just keep a track of how many are correct predictions. So correct is equal to 0. Now, so I will just do correct, I will increment if it is actually equal to my ground truth. This sum is required if you have batches. So I need to sum of all the positive true values across the batch. Let's say I'm doing the evaluation on a batch of 10 images. So out of 10, 7 are correct. So this sum will give me 7 here. If you are having only one image per batch, you don't need sum here actually. So that's what I'm doing it here. So now once this is done, so for all the dataset, for the whole test dataset, it will do the computation and it will calculate the correct elements. Now the accuracy computation is, so correct divided by now length of data loader. So this is required because we might be loading in batches. So we need to know how many images are actually available. So for that, the length of test loader will give me how many batches are there, and I need to multiply with the batch size. So let's say I'm using batch size of 16 here. Okay. So while loading the dataset, I will show you how to load them in batches. So for now, just assume that I'm loading in 16 batches, right? So now this is my accuracy. If you see, what we are doing is how many are total correct predictions and what is my total dataset. Now I will print this accuracy here. So I'm using f strings. So this will give me the accuracy directly. So this is my evaluate function. Fine. So yeah, that's it. I think this should be good enough for our model. So now let us actually initialize the model. So I am doing model is equal to capital model. This is what I have initialized with, right? Yes, capital model. So I'm sending the sizes. So I'm just sending 128, 64, 10. This will initialize my model. Okay, done. Now we have the data sets available here in data train and data test. So as I mentioned in the accuracy calculation, we can use the batches. You need not to send only one image at a time. So for that, we have a data loaders available in PyTorch. So we can actually use the data loaders as part of PyTorch to actually load the data in however we want. So while loading the data, there are many factors. You might need to shuffle the data set, or you might need to cache some of the data set, or batching is one operation. So all of these things you can do using this data loader. So we have to import this. So now I'll just mention batch size. Batch is equal to 16 because I have used 16 here. So I'm using the same batch size here. If you don't want to hard code, you can actually send the batch size as part of this evaluation function in the function call. Now I need to create the data loaders for training and testing separately. Train data loader. This data loader of, so whatever my original train data set is there, whichever I have loaded into, now batch size is equal to batch. If I want to shuffle the data set, I can actually do shuffle. So these are the data loaders. So you understood the difference, right? This, while loading the data set, you just need to compose it and load it. So here you need transforms. Whereas when you want to actually load the dataset with the batch sizes or shuffling the dataset, caching it, repeating it, so all these things you can do using this data loader function. So we need this data loader function. Okay, now I want to train the model. We have loaded the dataset, we have built the model, we have built all the functions required for training and evaluation. So now I need to train the model. So for that I'll just do tqdm for giving me the bar kind of visualization for the progress. Now I can keep how many epochs I need. So maybe I can train for 10 epochs. So here I am writing the training loop. I need to load the dataset one by one, right? So for x comma y in tqdm of, so what is my dataset name? Train data loader. Yes. Now in tqdm I can actually put the string function for the logging. Now for x and y, I need to actually pass to the model. So model dot fit. So if you see in our definition, we have created a fit function which will do the actual training loop for a particular image batch. So here I am sending that batches one by one. Dot fit one by one. So it will give me loss as the output, right? So it will give me loss as the output. So now I want to take the total loss for the particular epoch. So I'll just do total loss is equal to 0. Now once I get the loss here, I will do total loss plus is equal to loss. So I am adding the loss for every iteration inside the epoch. Now once this total loss calculation is done, average loss I will calculate. Average loss is equal to total loss divided by length of your data loader. How many batches you are having. So this will give me the average loss per batch. So I will print this for every epoch. So this is my training loop. So now let us start and train the model. Okay, so the model is getting trained here. So it will run for 10 epochs and it will print the loss information for every epoch. So you can see for epoch 0, the first epoch, the loss is 2.2. The loss should be decreasing from one epoch to another. So here you can see that it has finished all the epochs, 10 epochs, and the loss, it started with 2.2. By the end of 10th epoch, it has reached 1.68. So this is the loss. So the training is done. Now we will see the evaluation part. So for evaluation, we already have a function named evaluate. So we wrote the function here, right? So we'll just call that function evaluate. So model dot evaluate with the test loader. So this should give me, this should actually evaluate the model and give me the accuracy percentage. Yeah. So it has evaluated and it has given me the accuracy as 79%. Okay. So this is from model training and evaluation. Now if I want to save the model, how can I save the model? Because I don't want to lose this trained weights, right? because I want to load the model in some other machine or like that. You know what is the purpose of saving the model. So if I want to save the model, I can save the model with save function. For that I need to give the name of the file, like the full location where you want to save the file. Let's say I want to save mnist model.pth, and I will save in this folder only. If you have some other folder in your machine where you want to save, you can give that path here. And PyTorch has save function. So torch.save. Now this will actually save the model. And what is your model actually? It is a model. This is my model object. Now you can actually save, while saving the model you have different options. You can actually save the whole model along with the architecture and weights, or you want to save only weight values. Let's say you want to save only weight values, then you can only save the stateDict function. So this is where the model has all the weights. So now this one, it will only save the weight values. Only weights. So if you want to reload this model, we need to first define the model in our code and then load it once you get the model instance. Otherwise it won't work, right? So this is only for saving the weights. So let's say I'm saving the weights here. Now if I want to load these weights, first I need to do model2. Let's say I don't want to take into the same instance. So this is model 128, 64, 10. Okay, you should be having the same model because the weight mismatches will happen if you initialize a different model. So now I have initialized this particular model. Now I can actually load it. So for loading it, I can do load stateDict. So wherever path is there my model, I am actually loading that from the torch.load, and I am loading those state values or weight values into my model. So this is what I am doing. So if you are saving only weights, for loading this one, you have to actually initialize the model first. So you should have your source code of the model. This is how you can do. Now if I want to do model2.evaluate, I'm not training, I'm just evaluating it with the test data loader. It should give me the same percentage. Oh, sorry, I made a mistake. It should be model_2. Okay, I have loaded the weights. I'm evaluating it. So yeah, it is giving me the same percentage. This is how you can load. So there is another way. If you want to save the whole model, I don't want to keep the source code everywhere. I want to save the whole model. So for that, maybe you can keep path is equal to, I'm just keeping full model.pth. Okay, so this is my full model. So for this, I can do torch.save the whole model instance as it is, and then object path. That's it. So now I am saving the whole model here. This is actually full model with architecture and weights. Okay. So now if I want to do model 3, I can directly do torch.load of path. Okay, so I need not to initialize the model. I don't have a source code. So I can show you model3.evaluate test underscore data loader. Okay, so if you see, this is also giving me the same thing. So model 3, if you see, I did not initialize it as model here. I'm directly loading it from the path because it has the architecture also. You need not to have the source code available with you. So this is best if you are deploying in Dockers or some other environments where you don't want to keep the source codes. But memory wise, this will take less memory for saving the model because this will only save the weight values. So if you want to understand the batch concept clearly, so let's say like how the batch 16 is happening, right? So I'll just show the one sample prediction and comparison just to show you how it works. So let's say I want to, this is actually testing I will take. Test data loader. Now what I need to do, I'll just do the prediction once. So for that I can directly do model dot predict of x. So now I got x and ground truth prediction. So it is y, this is my ground truth, and y prediction. So I'm just taking only one part. So as I mentioned, my batch size is 16. So this x will have 16 images and y will have 16 labels. And the same way predictions also 16 predictions will come. So if you want to see this output, you can actually see here. So these are 16 ground truth values and these are the 16 predictions from the model. So this is what we are comparing both. And if you want to compare both, right, what will happen if you want to do y equal to y prediction, it will give me the truth table, true, false, like that. Wherever it is matching, it will actually give me true. Wherever it is not matching, it will actually give me false. Now if I take the sum of these, it will give me the total truths available. So that is what we are doing in the evaluate function here. This sum we are taking so that we are getting how many correct predictions are there. So yeah, that's all from this video. Hope you have learned how to build any network in PyTorch. The process is similar for PyTorch or TensorFlow or NumPy, any toolbox you are using. It doesn't matter. For model training, you need the dataset first. After that, you need to build the model and you need to write the functions for training as well as evaluation. So those are the things we have done here. And if you want to do some other data analysis like exploratory data analysis, EDA, you can do so many things. You can write the functions here once you loaded the dataset. Here you can analyze your data and based on that you can make decisions on your training parameters. That's all from this video. Thank you.